So you've hopefully at this point you've got a graph, and now we're going to look at what those graphs look like and what we can learn from them and what we actually mean when we talk about a thing called Boyle's law. Okay, so let's scroll down. Let's bring this one first up. So if you first plotted the pressure of the gas on the y-axis against the volume on the x-axis, then you end up with a graph that sort of is this nice starting to curve. And this is a kind of shape you get whenever you plot. So if you plot it's called a pressure volume graph. That would help if I wasn't. I don't know what I've done there. Oh, it's because I've not got my thing that tells me I'm not leaning on it. Oh dear, that's all very exciting. Go away. Right, so let's have that. So if we plot, that's a terrible line. So there's volume, there's pressure. You get something that starts to look like this. Okay, so it's this kind of curve. It may be a graph you may have seen something looking a little bit like this in maths at times, but if you haven't, don't worry, we'll talk about it. But this is essentially a curve that's sort of an inverse relationship. It's because what happens is that as volume, as our volume gets bigger, our pressure gets smaller, and so on and so forth. So if pressure increases, then volume decreases, and vice versa, because it depends on what you're doing. You can and this is actually how your lungs kind of operate, because if you think about when you breathe in, what happens is that you breathe in, so you increase in a big inhale, you increase the size of your lungs, so that means that your volume will go up, your volume increases. That causes the pressure of the air pressure inside the lungs to fall, which is therefore what leads to air rushing in to fill that space, to equalize the pressure. It's all about equalizing pressure. You are not doing anything beyond expanding the volume of your lungs to suck air into your lungs. Okay, that's a sort of a limit to what that can be. So this is sort of what we now Boyle saw this, and it's nice that we've got this curve. We've got a nice curve. Points are falling on this line. That's all lovely, but it's not immediately obvious what the relationship is, because actually there's lots of graphs that you come across that may take this shape, that may have this sort of curved nature of it. And so what Boyle decided to do is to try and find the relationship, and that was the second graph you were asked to draw, which comes out as a lovely straight line, because you plotted this. The pressure against 1 over the volume. And look at it. What a lovely straight line. I mean, that not only does it make me happy, it makes me rainbow happy. This is a rainbow smiley for this one. Yay. That is how awesome a straight line. The straight line on a physics graph is the pot of gold at the end of the rainbow. So what this means is that when Boyle came across this meant he had a relationship. Okay, and I'm going to talk a little bit about some maths about where this is going. So what is a straight line? And so I'm going to make a little sort of maths thing. So imagine these aren't pressure and 1 over volume. Don't worry. Imagine they're just sort of y and x. Well, this graph, you ever saw this in maths? Okay, this would tell you that if you had a graph like that, so you've got y and x, and you had a straight line through the origin, you would say, oh, okay, y is directly proportional to x. And you might remember from maths that what you can do with that is to say that y, and I've just forgotten how to write y. That was terrible. Lambda. Let's go back to that. So that means that y, I've literally done it again. Why have I just... that's the techno, you fool. You fool! There we go. Y is equal to some constant times x, and that's sort of a little matrix. So this is a constant. It's got a value. Okay, that's what this kind of thing tells you. It's a constant gradient, so on and so forth. But for what that also means that we can sit there and say that, okay, well, that would mean that y divided by x that is equal to some constant. So any sort of values that you have, if you pick any of the values on the line and you do y divided by x, you end up with a constant. Okay, that hopefully is an idea you've met at some point in maths and you've come across. And I'm going to put that over there. Because Boyle realised you can apply the same thing, but instead of y and x, you've got the pressure the gas is under, and you've got 1 over the volume. Okay, but let's apply what that means. Okay, we can apply the same. We get a straight line through the origin, which is lovely, and we can say, okay, we know that pressure is therefore directly proportional to 1 over the volume. So what does that mean we can do? Well, we can say that therefore, using the same logic that we've met before, is we can say that pressure is proportional to 1 divided by the volume, because that's how we get our straight line. We can therefore say that pressure is equal to some constant divided by the volume. Same trick as we've got done up here. It's just the fact is that we've got 1 divided by something. So if we then rearrange that, that would lead us to this idea that pressure times volume equals some constant. I'm going to actually even write out constant with a K because cool times. So this is what this graph told Boyle, is that for a fixed mass of gas, the pressure multiplied by the volume should always give you the same number, depending on some other things. So let's go and grab our data and let's see if that holds. Okay, so we're gonna test whether Boyle's correct here, given this data. So we've got a pressure of 1, we've got a volume of 44 cubic centimeters. So all we're going to do is we're going to go down this line and we're just going to multiply these things together and see what we get each time. So starting with the easiest one, 1 times 44 is 44. So we can say that is therefore 44. Next one, 2.55 times 17. So we've got 2.55 times 17 and 43.4. Okay, I'm quite happy with that. That's quite close. 43.4. 2.1 times 20. 42. 1.9 times 22.5. And that gives us 42.8. 1.6 times 27. We've got 43.2. 1.25 times 35.5. We've got 44.4. Okay, and finally 2.95 times 14.5, and we've got 42.8 again. And look at that. They are all, hopefully you can agree, given that this is experimental data taken from an experiment where we do obviously always have some measurement uncertainty, this is holding. Okay, so that tube that you saw, no matter what pressure I put it under and volume it is, if I multiply those two numbers together, I will always get 44. And so if we ever have a sealed sort of container, say a balloon or an air bubble or anything, and if we've ever got some kind of sealed volume of gas at some pressure, what that means is that if we change the pressure, then the volume is going to change so that when you multiply them, you always get the same value. You always get a constant. So there is something that's changing, which means that we could maybe make a prediction. We could say, well, what would happen? How big would this be if, we would say, so this comes out as being, I'm going to average all these out. I'm doing that in my head, but I'm going to say that's approximately 43. Let's go with that being an average of about 43. If we say, well, whatever we do to one thing, we would always get pressure times volume equals 43 for this situation for this mass of gas in this in that temperature. Or we could say, okay, well, what would happen if we, like, let's say we turned the pressure and we made it 4.1, or we'd say, well, what would happen to the volume? Well, we'd end up with 4.1 times the volume would have to equal 43. So we'd end up with a volume of 43 over 4.1. And we end up with about 10.5 centimeters cubed. So what it allows us to do is to make this prediction. Okay, but there is a sort of like an assumption. The assumption is, remember, that we've not changed the temperature and we've not allowed any gas into or out of our little tube that's gone inside. So that is Boyle's law, that for a fixed, so I'm going to just have that sentence, this is what it is. So for a fixed mass of gas at a constant temperature, the pressure times the volume is a constant. And that is Boyle's law. And we'll look at how we can solve that mathematically and some practice problems next lesson.